Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. We are discussing about the waves in this part of the programs. Especially, we are now in the topic of velocity of wave in different medium. Before we start this session, let us see the outline for this lecture. In this lecture, we are going to get an expression for the velocity of the longitudinal wave in a material medium. We are familiar with the propagation modes of waves like transverse wave and longitudinal wave. In one of the earlier lectures, we have arrived at the expression for velocity of a transverse wave that is set on a string. We have arrived at the expression for the velocity and concluded that it depends on the physical properties like the bulk modulus, which is the elastic property of the medium, and also the density of the medium. This lecture is specially devoted for the same kind of discussion to arrive at the velocity of the wave, but for the longitudinal wave. Before we start the derivation, let us brush up how the longitudinal waves propagate in a medium. We very well know the technicalities like compressions, rarefactions and the direction of propagation, etc. If you have a look at the method of propagation of a longitudinal wave in a medium, we will be able to get the required knowledge so that we could continue with the derivation for the equation for velocity of the longitudinal wave in a medium. So, let us have a look at the method of propagation of longitudinal wave in a material medium. This picture shows how the particles are moving to and fro and what is the direction of propagation of the wave. The wave is propagating to the right, but the particles are just oscillating. This diagram shows the snapshot case still taken at an instant. This shows the wave is propagating as compression and rarefaction. The compression has got higher pressure region and the rarefaction is the low pressure region. So, this is how the waves propagate. We are familiar with two terminologies as far as the propagation is concerned: the velocity of particle and the velocity of the wave. In longitudinal mode of propagation, the particles vibrate in the direction of propagation of the wave. Hence, the particles are getting accumulated at one region at an instant and it is rarefied in another region, and so on, it is continuing successively. So, we have regions of compression at various locations and equally the rarefactions in between, and it is a temporal situation. The next moment the region of rarefaction will become region of compression and the region of compression will become region of rarefaction. So, this process will continue. So, every particle will have this region passing on it. Actually, the particles are only making the region become compressed region or rarefied region. Now, a second logic that we have to keep in mind is because of this compression and rarefaction that is produced, the pressure in the region is also getting changed, and thus the density also is momentarily changing. The wave itself is propagating actually as a pressure wave. We have discussed this concept already. The pressure wave is having a slight phase difference with the actual displacement wave. All these are familiar. So, with this knowledge that we have got about the propagation of longitudinal wave, let us make an attempt to get an expression for velocity of the wave. Let us start the discussion for the velocity of longitudinal wave that is said to propagate in a medium which is contained in a long tube. The medium could be a liquid medium where also the density is going to change because of the longitudinal wave propagation, or it could be a gaseous medium. It is applicable for both. So, let us take one such case and take our discussion further. Consider a long tube of area of cross section A. Let A and B be the two cross sections of the tube. Suppose in the region of normal density, the medium moves from right to left along the length of the tube with velocity v, and the sound waves travel from left to right with a velocity v. So, this is the situation, this is the case. In a long tube, the medium is said to move forward and backward, but the wave is meant for movement in one direction, it will always move forward. So, the wave is propagating from left to right for our discussion, but at the instant that we consider, the medium is moving from right to left. Let us see an illustration that shows the movement of the medium as well as movement of the wave. Let us have this illustration. So, this is a simple illustration. In a tube, the sound is propagating. The velocity of sound is directed from left to right. At an instant from right to left it is moving. So, these are the two sectional regions, areas of cross section. A and B are the regions. Small a is the area of cross section of the tube that was mentioned in the material we have seen earlier. Because of the to and fro motion, we have different quantities. The P is the pressure, V is the velocity of the sound, and rho is the density of the medium. So, we have the same situation for the region B also. So, these are the data we are going to use for our discussion. We have different values of pressure, density and velocity in the two cross sectional regions A and B. Let us see how these values are taken at an instant, which part allows the medium to come in, which part allows the medium to leave. Let us see. In such a case, the positions of compressions and rarefactions in the tube with respect to the ground will remain fixed at an instant. For any small region, the pressure, velocity and density of the medium remain constant. The values of pressure, velocity and density of the medium will be different at different cross sections of the tube. This is also an important point that we have to keep in our mind. When the wave is not propagating, when the medium is not disturbed, the whole region has the same density, the same pressure and other quantities, a homogeneous medium. But because of the propagation of the wave, temporarily at some regions the density is higher than the normal value, and at regions equally it is lower also in some of the other regions. So, this disturbance is caused because of the propagation of the wave. So, the medium is a homogeneous medium, but when the wave is propagating, it is causing disturbance. Because of that, the density, pressure all are varying. That is what we have to keep in mind. Let us see the concepts further. Let A correspond to the region of normal density and B correspond to the region of compression. Bring back the illustration we had just before. A is one cross sectional area which is on the right hand side of the tube, and B is the cross section which is on the left hand side considered. So, these are the two regions. At A the pressure is P and density is rho and velocity of the medium is V. At B the pressure is P1, density is rho 1 and the velocity of the medium is V1. There is no change in the average density of the medium. The masses of the medium crossing the section A and B in 1 second are equal. We have taken a small cross sectional region between A and B. The volume is very less, so that whatever medium is entering in the region of A and whatever is leaving the cross sectional region, cross sectional area of B, both are same, but the velocities will be different. That we have to keep in mind. The velocity with which the medium entering and the velocity with which the medium leaving will be different. Because of that, the pressure and the density values will also be different, but the mass will remain the same. What mass is entering in the cross sectional region A and what mass is leaving the cross sectional part B, they both will be the same. So, this is going to help us to utilize some of the expressions for simplification at a later stage. Let us go ahead with the derivation further. The mass of the medium crossing the cross section A in 1 second is given by this expression A multiplied with V multiplied with rho. Here A is the area of cross section and rho is the density and V is the velocity with which the medium is entering into the region A. When we multiply this V and the A is the area of cross section, V is the velocity, that is distance in 1 second. So, this will give us the volume, and with which if we multiply the density we will get the mass. The same is adapted for the region B, and in the region B the mass is the leaving mass. In the region A the mass is entering and in the cross section B the mass is leaving, the medium is leaving. So, what is the mass that is leaving? That we have assumed as the same, but the expression is slightly different. Let us see what it is. The mass of the medium leaving the cross section B in 1 second is again given with the same logic that we have discussed for the cross section A. It is the area of cross section A. Here the velocity is different, so it is denoted as V1 and the density is denoted as rho 1, but this product will also give the same mass m, because the mass entering the region A and the mass entering the region B both could be equated, and after the two terms are, the two expressions are equated, we get a equality. That equality will be used for further simplification. Let us see what it is. We are equating the two masses and in which the area of cross section is the same. So, we cancel that and this gives us the product V rho and the product V1 rho 1 as equal. Here V is the velocity of the medium with which it is entering, rho is the density in the region A, and V1 is the velocity with which the medium is leaving the cross section B, and rho 1 is the density in the cross section B. So, we have taken up for discussion how the medium is moving in the two cross sections that we have considered A and B. Now, the change in density is obvious because the particles are vibrating with different velocities. Let us see further how the derivation is carried forward to arrive at the final expression for the velocity of the longitudinal wave itself. Now, let us see further. If B is a region of condensation, its density will be higher than the normal density rho at A, because A is the normal part and at B only we have the compression or condensation, both are having the same meaning, condensation or compression both convey the same meaning. If that is being the case, the densities are different. So, with which we are denoting the rho 1 is greater than rho, and similarly the velocity v1 is less than v. So, what does it imply? In the region A the density is less, and in the region B density is more, and when we take the velocity, in the region B the velocity is less and in the region A the velocity is more. When we say the velocity, it means the velocity of the medium. Now, we have two terms, what is the mass that is entering or leaving that region and with what velocity it is happening. We can make an attempt to find out what is the momentum of the medium in the two sections, and further is there any change in the momentum. We are going to investigate in that line. So, let us see what about the momentum that is changing in the two cross sectional regions A and B. Let us see. The momentum per second of the medium at A is given as mv. The momentum per second of the medium at B is given as mv1. We have taken the mass entering and leaving both as same. So, in the both expressions we have the same mass, but their velocities are different because they have different velocities of entering and leaving. Definitely there is a change in momentum happening in the two regions. So, now we take the derivation further to find out what is the change in momentum that is happening per second. That will give us the relation for the force itself. The rate of change of momentum is force. So, we are moving forward in the direction of finding the force, but before that what is the change in momentum? Let us see the derivation further like this. The change in momentum per second could be taken up by finding the difference between the two terms. This change in momentum per second is due to the difference in pressure, which is represented as P1 minus P2 between the two cross sections A and B. Since the tube has an area of cross section A, small a, the force applied is F is equal to the area of cross section small a multiplied with the difference in pressure. We very well know the force could be obtained by multiplying the pressure difference and the area of cross section. So, that is what is done here. So, the final expression for force is arrived like this: F is equal to the area of cross section multiplied with difference in pressure. According to Newton's second law of motion, the rate of change of momentum is equal to the applied force. So, we are equating the rate of change of momentum, which is taken on the right hand side. On the left hand side we write the expression for the force that is applied. So, we have got an expression for the applied force due to the pressure difference and also the rate of change of momentum. This is written according to the Newton's second law of motion, which is called the law of momentum. For any rigid body, the external applied force will produce a rate of change of momentum that finally arrives at the mass multiplied with acceleration. For in mechanics the concepts go like this, but here we just use the second law of Newton's laws of motion for our derivation, which would lead us to an expression for velocity of the longitudinal wave. Now, let us take up this final equation for further simplification. That is what is done next. Hence, we have equated the two terms, the applied force and the rate of change of momentum. Mass is constant, so it is taken out, and here the V is also taken outside the bracket, the simplifications are done as normally done in the case of any mathematical derivation. Now, substituting the value of mass which we have already got for the region A, it is taken as the mass that is entering as the area of cross section small a, the velocity of the entering medium V, and the density rho. So, when we use this relation, and also one more relation we have got, rho 1 V 1 is equal to rho V, that is rewritten, and these two are used here to replace this mass. We have used this expression, and to replace this V 1 divided by V 2 we have used this rho divided by rho 1. So, the final expression is taking this form, and what is very important for us in this expression is this is the velocity with which the medium is moving to the left, and thus the wave is moving to the right. That is the assumption we have made. So, we have brought in the velocity into the expression. Now, we have to simplify further so that this velocity could be written in terms of some of the measurable quantities. Though we have written the density, the pressure difference, these quantities are little difficult for us to measure because they are changing, continuously changing. At instant the temporal value will be very difficult to find. So, we have to replace some of the difficult terms with easy measurable terms. So, that is what we are going to do in the next stage. Let us proceed further. The further modification to the earlier expression gives us this form. We have rewritten the previous equation, and in the numerator we have the pressure difference, and in the denominator we have a relative change in the density. This is called the change in density, and we have the original value. So, this is called the relative change in density term, but we very well know the definition for bulk modulus of any given medium. The bulk modulus is a important physical property of any medium. So, for bulk modulus we have stress in the numerator, and in the denominator we have the strain. The ratio of bulk stress to the bulk strain will give us a physical parameter called bulk modulus. So, we are bringing that equation here to modify the equation for velocity of the longitudinal wave, which would have some of the measurable terms. So, that is what is our next attempt. Let us go further with simplification. So, for the bulk modulus we use this equation. When we compare this equation with the equation on top, the pressure difference is same in the numerator. In the denominator we have the relative density, change in density, and here we have relative change in volume. So, is it possible to replace the velocity, the volume term with the density terms? So, that is our next attempt. What is the relation between the density and volume? Between density and volume the ratio is inverse ratio, the inverse relation only we have. So, with which we can even easily replace the change in relative density. So, that is what is done next. See here, the volume is inverse of the density, and accordingly we have replaced the density terms with the volume terms. Hence, the bulk modulus itself takes a new equation. Instead of volumes here we have the density terms. Now, this could be used in the original equation for the velocity of wave which we have arrived at. Let us see how the velocity equation is modified with the bulk modulus term included. See, once it is done, the velocity of the wave becomes a very simple equation here the V square is written as the ratio of bulk modulus to density, the velocity of the wave becomes V is equal to square root of the bulk modulus divided by density. So, we have arrived at the final expression for the velocity of the longitudinal wave in a medium. The velocity of the longitudinal wave depends on the physical properties like bulk modulus and the density of the medium. We have to keep this in mind. It depends on two physical properties. One is the elastic property, the other one is the bulk property. The bulk property, I mean the density. For a homogeneous medium, in an undisturbed condition, there is a constant density throughout, and similarly there is a constant bulk modulus throughout. So, these are the two factors on which the velocity depends. Velocity of the sound or the longitudinal wave depends. These two factors are very important. When we say modulus, bulk modulus, it is an elastic property which tells how far the medium could be deformed. Here when we say the medium, it means the particles present in the medium, how far they can be deformed, they can extended. So, one is the elastic property. This tells how far the particles could be displaced or deformed. The second factor, density, tells how far these particles are packed together. So, that is the density term. So, how much it could be deformed, how much the medium is denser, how much the particles are kept closer, what is the density of the medium. So, on these two properties the velocity of the longitudinal wave depends. Though we have taken the velocity of the medium as V, that itself is the velocity of the wave, how far the medium moves, the same way the velocity of the wave itself is moving, because the movement of the medium is the movement of the wave. That is what we have already learnt. And at this juncture I would like to mention another important factor which we have already learnt, that is, we have derived an expression for velocity of the transverse wave in a stretched string. For that also we have got the similar expression. The velocity depends on the elasticity and also the density. So, what is the conclusion? Whether the wave is a transverse wave or a longitudinal wave, it depends on the physical properties like the elastic property and density of the medium. This could be extended further for the gaseous medium. The medium that we have discussed here could be a liquid medium or even a gaseous medium, but in a air medium, how the equations could be modified for accommodating the velocity of sound, that we have for the future discussion. And I would like to conclude today's lecture with the session summary of today's lecture. Let us see what is the session summary. In this lecture we have seen the concepts of velocity of a longitudinal wave in a medium, either a liquid medium or a gaseous medium. Before we wind up this session, let us test our understanding by answering these questions. Explain how the longitudinal waves propagate as pressure waves in a medium. Derive the expression for velocity of longitudinal wave in a medium. Discuss on what factors does the velocity of longitudinal waves in a medium depend. I would like to conclude this lecture with the statement that the velocity of wave depends on physical properties. Thank you for watching.